So today I'll be talking about Nodeless Kubernetes. It's something I work on at a Lodal, and I'm hoping to tell you why you should run Nodeless Kubernetes or add Nodeless Kubernetes to your Kubernetes cluster. Once I sort of give you the idea of why it's worthwhile to run Nodeless, we'll take a look at two Nodeless Kubernetes solutions. The first of those is virtual Cubelet, and the second one is Milpa. It's a shameless plug. I work on Milpa during my at work, so we'll check that out. We'll get into the weeds of how those fit into your Kubernetes cluster and take a look at some of the technologies we've used and exploited, and then we'll do a demo, and hopefully we'll have some time for questions afterward. So I'm not here actually because of Kubernetes. Kubernetes is simply the de facto infrastructure management solution that we have right now. I'm here because I believe that computing should be cheap and easy. Easy is why we moved to the cloud, actually. It's why we're on AWS. Moving out of our own data centers and into AWS allowed us to outsource a lot of the trouble of running on-prem, and it allowed us to develop software faster and deliver in shorter time frames. And as such, our software development cycles became cheaper, actually. So I'm going to show you how Nodeless Kubernetes makes computing cheap and easy. So the model for a lot of cloud computing, like EC2, grew out of sort of the ideas from on-premise computing, where you had a lot of servers and your whole goal was to make the best use of those servers. You didn't really grow or shrink elastically because you had physical hardware that you had. But the cloud offers us thousands of on-demand virtual machines, and this allows us fantastic scalability. These machines in AWS, it's great actually, it's a very nice cloud. They have fast startup times. You can usually get a machine and up and running in less than 30 seconds, usually less than a minute. Tons of different machine types, specialized hardware. You have on-instance SSDs, GPUs. It's great. The burstable T instances, where you pay per millisecond of CPU used, are really, I don't know another cloud where you have that functionality, and that can really help you control costs when you don't know, when you have bursty workloads, for example. And finally, spot instances, we all know, can help save you a ton of money, up to 80% on your cloud bills, if you can withstand some disruptions in your computing. However, despite all these things, and despite these scalability aspects of the cloud, we're still using it a lot like an on-premise data center, where you spin up a machine, you provision it, and it runs for weeks, months, sometimes years. And Kubernetes is it really comes from the on-premise mindset as well. And that's a good thing. It's actually helping a lot of companies get out of their data centers and migrate to the cloud by providing a standard infrastructure that they can use and program against. But because of its model, the whole way of provisioning a Kubernetes cluster is you provision the control plane, and then you provision your worker nodes. And now we get into capacity planning, where how many nodes do you need? What type of nodes? Should they have specialized hardware? How many of those do we need? So capacity planning is actually quite hard. If we provision too many nodes, well, then we're overspending on our cluster. It's kind of like a really expensive gym membership when you don't actually go to the gym a lot. You could have just bought maybe like a spin class or signed up for a yoga class and paid when you used it. If we provision too few nodes, that's actually worse because our workloads won't run. We could actually be taking down servers that we have, services that we have. And if we want to use rolling updates, horizontal auto-scaling, batch jobs, and all those, well, we really have to provision our cluster for the high watermark of our usage. And we have to know where that is. These are hard things. So There's a few ways around this. People typically have said, okay, well, what we can do is we can make one big Kubernetes cluster and pack everything onto there, and hopefully the varied workloads will end up smoothing out our demand. But it usually doesn't work that way. A lot of our apps are strongly correlated with each other, and they need to scale up and scale down at the same time. This also has the unfortunate effect of your blast radius gets really big. So when you mess up, your Kubernetes cluster goes down, you're no longer taking a team's services down or something like that. You're taking your entire company offline sometimes. And there's various failure reports of that actually happening. And that's a little sad to see. So you don't need the headache and the sweating and all that of running a big, or you don't want the headache and the sweating of running a big Kubernetes cluster. Now, the cluster autoscaler, however, that's a great piece of technology. Lets you scale your cluster, and but you have to get the knobs right. It's not too easy to do, but you can do it. You need to manage your node pools, and scaling up is pretty easy. If there are pods waiting, we scale up our cluster, and they run. Scaling down, though, is a little bit more complex. You have to deal with disruption. If you have persistent volumes and other things, maybe we can't get rid of that node. And oftentimes you see people complaining that despite the cluster autoscaler's best efforts, we still have hot nodes and cold nodes. And so we're still doing bin packing onto these nodes. And we need to really kind of like target the right machine for our workloads so that we don't have just like a node running at 20% capacity or something like that. So oftentimes, even though you're using the cluster autoscaler, your nodes and your cluster are still underutilized. So instead of cheap and easy, it's kind of like pick one. Do you want cheap or do you want easy? And that's the typical way that we see in a lot of Kubernetes. But what if there was another way? What if we got rid of the things that are causing our capacity planning woes? What if we got rid of the nodes? This is kind of taking a page out of serverless, where what we actually do is we want something where we can provision compute at the time that we need it, and it's right-sized for what we do. It scales up when we are running our workloads and scales down when we're not. If only there was a service where we could have containers do that for containers. Like serverless is usually running functions as a service. That's like kind of the connotation of serverless. But there's also Fargate. Fargate's great. It's a container as a service backend. You guys probably are familiar with it. And it has very low overhead cost. Doesn't require you to do any capacity planning. Has fantastic scalability. It's cheap and it's easy. If we could use this in Kubernetes, that would be great. It's AWS specific, but we're at AWS Community Day, so I take it we're all on AWS and happy. So can we plug this into our Kubernetes cluster? Well, when Fargate came out in 2017, Fargate in EKS, if you read the blog posts and things like that, it was just right around the corner. Oh, it's gonna come soon. And reInvent 2018 rolled around. Fargate in EKS wasn't announced. And so we still have no Fargate integrated into EKS. This open issue in the AWS Containers Roadmap is probably just gonna sit there for a while. There's reInvent coming up, so maybe 2019 is the year. But in the meantime, maybe we can run it ourselves. Maybe we can fit Fargate into Kubernetes on our own. And that's where Virtual Kubelet comes in. Virtual Kubelet is an open source CNCF project. Virtual Kubelet pretends, as you can tell by the name, to be a kubelet. And it impersonates a regular Kubernetes node. So it understands and speaks the API server to Kubelet API. However, Virtual Kubelet, when you dispatch a pod to it, instead of running the pod on the local OS, it runs it on Fargate. So it's responsible for translating between your Kubernetes manifests, or pod manifests, and Fargate. And when you run Virtual Kubelet in your cluster, we can see it's right alongside other nodes here in this wonderful pictorial diagram. It looks exactly like another node. It responds exactly how the API server expects it to, telling it its node conditions, what operating system it's running, et cetera, et cetera. But instead of actually running things locally, it's dispatching it to Fargate. It's a great piece of technology, great software, and it really lets your workloads or your compute costs scale with your workloads. I really like it. It's cheap and it's easy. And unfortunately, it's not ready for production yet. This has been in the README on the Fargate AWS provider for virtual kubelet since like the very beginning, and I just checked last week. It's still there. I'm not sure why it's not getting the attention that it needs, but basically it says, don't let this anywhere near your Fargate cluster or your Kubernetes cluster, and that's too bad. Hopefully, maybe they can do a little bit of work and sort that out. It just hasn't been getting the development it needs. So that's the state of virtual kubelet on AWS and Fargate. Now next up, we have Elodel's Milpa. Now this is a software that originally was designed to be a nodeless compute engine. You tell it to run containers, and in the background, Milpa would dynamically provision VMs and dispatch those containers onto the VMs. We decided that, oh, well, this would be a pretty cool thing to fit into Kubernetes. So we wrote Kiot, which implements the CRI, that's the container runtime interface. It's a fairly low-level interface that the Cubelet uses to run containers on the host system. So Kiot, so the Cubelet talks to Kiot. Kiot talks to our software Milpa, and Milpa runs the pods. And the interesting thing about this setup is each pod gets its own VM, and the size of that VM is based on the resource requirements in your pod's manifest. And you end up with strong VM isolation of your pods because of that. Each one is dispatched to its own VM. So looking at how this might be implemented, here we have a picture of your kind of standard one node Kubernetes setup. We have master on top. And in your typical setup, your API server is going to dispatch a pod to your Kubelet node. The Kubelet talks to the container runtime. And example container runtimes are like Docker, containerd, cryo. And it talks to the container runtime using the CRI. That's the green arrow there. And some example CRI calls are shown up in the upper right-hand corner of this slide. And then the container runtime talks to the operating system to run those containers. It's going to create namespaces, it's going to create C groups, it's going to start processes, and these are the wonderful things that we know as containers. So with Kiot taking the place of our standard container runtime and Milpa taking the place of our operating system, when the Kubelet sends CRI calls to Kiot, Kiot's going to talk to Milpa, and it's going to spawn a virtual machine in AWS by talking to the AWS API. When it creates containers on part of the CRI, it's going to tell it, hey, create this container. All right. Escape. Oh, no. How do I get out of this? So, can you all see this? Do I need to make it a little bit bigger? Oh, it's a little bit down near the bottom. And I'm tethering because my internet doesn't seem to work, so this will be interesting. Let's make this a little bit bigger. Okay, so what we're going to do is, oh, this is going to be interesting. Can I just, oh, great. All right, we're going to run Docker coins, which is kind of a classic Docker microservice application. You might have seen this before. Consists of 5 microservices that all talk together to mine a fictitious cryptocurrency, Docker coin. And we are on a 2-node Kubernetes system. One of those nodes is the master, and then we have a Milpa worker. Looking at this, hopefully you can see this. In the AWS console, we have this. We have 2 nodes and a kube proxy running. We're not going to talk about that. So let's take a look at these nodes real quick. I'm curious about the worker node. What just happened? Oops, wanted to do a describe. So, interesting thing about how we do this is this node appears to have 1,000 CPUs, 4 terabytes of RAM, 10 GPUs. Typically, this would cost us a lot of money. We're a small startup. I think we'd run out of money in about an hour or so. So, what it actually is it's a T2 medium in the cloud. Because we have the whole scalability of the cloud behind us, we need to fake Kubernetes out to actually run this thing. So let's, or actually, we're going to apply our manifests, and I need to tunnel into this cluster. Whoa. Just let me set this up here real quick. All right, so we're back over here. Oops, and pods. Okay, so we're creating our containers. VMs are coming up in the background. We can see that over here in our AWS console. Okay, they're running. I bet that, let's see if we're up and running here. There we go. Yeah, we're running. And we're mining some Docker coins here. So even though these are running in different VMs in the background, they're all able to communicate with each other through standard Kubernetes means. But we think Docker is going to be, the Docker coin is going to go to the moon. So what we actually want to do is scale it up to, we want to mine more. So we're going to scale our workers up. And what we see when you do that is we didn't have to change the size of our cluster or anything like that. What we have, if you can see this, is we're just starting up a whole bunch of more VMs in the background. We have a custom resource definition, which will show those VMs as they come online. Now we have a whole bunch more VMs for our fleet of workers. And now it can take, since we're booting VMs in the background, it can take a few seconds for them to come up. Usually under a minute, they will be running. And what we can see here is we can see them start to come online, actually. Oh, is that hanging off there? Sorry. Yeah, so now our workers are coming online, our hash rate's gone way up, we're gonna make $1 million off Docker coins, but actually, you know, Docker's coins aren't actually worth anything. So let's scale this back down to 0, because, you know, that's kind of what we want to do. And now we see that our workers have gone away. We're shutting down instances here in the background. And yeah, we've successfully run through all of that. So what we saw was our compute scaling exactly with our workload, which is kind of like what I think computing should be and the promise that the cloud holds for us. So getting back to this presentation, where were we? Please start. All right. The key takeaways from this. Capacity planning is not easy. You can do it and make an effort for it, but nobody knows what the future holds. But Nodeless really lets you scale your compute with your workloads. And Kubernetes can be run in a nodeless setup. It doesn't come out of the box on most cloud providers, but you can do it. And 2 ways to run Nodeless on AWS is with virtual Cubelet, once again, a CNCF project, and Milpa. So something that you want to do is experiment. Try it out. Have fun with it. Yeah. And I have some references here. The slide deck can be found at tiny.cc/nodeless. If you make up words for your technology, you can actually grab URL shortener lines pretty easily. You can also find it at our Twitter and things like that. Virtual Cubelet's online, as is the AWS Fargate provider. You can find those repos. And we have a Terraform repo for starting up a nodeless Kubernetes cluster using Milpa. Finally, as thanks, Madhuri and Vilmos, they're in this room. Madhuri, Vilmos, are you here? Oh man, he might be. Oh, there he is. You can talk to them afterwards if you have questions, things like that, if I'm not able to answer them. Also want to thank Jerome Pettazzoni. He did one of the first Nodeless Kubernetes talks. Also, John and the rest of the community today volunteers. It's great that we could put this on. And the Computer History Museum. It's wonderful to be here.